Ladies and gentlemen, my name is Carl Glittenberg. I am the Global Medical Director for Topcon. I'm also a retina specialist, and I work as a researcher at the Karl Landsteiner Institute for retinal research and imaging. So a lot of the things that you are going to see here are a result of some of the research that I'm doing and me playing around a little bit with the data that we can collect using the Triton OCT, but some of it is not going to be actually on the machine at this point in time, just so that you know what I'm doing. But I'm just trying to use the data to show you what it is possible to do with the actual data that we're able to collect using this, this instrument. So if you look at this, this patient right here, you have a choroidal neovascularization, and at the top you have the OCT-A after about 5 injections of anti-VEGF, and you can see that you have a CFAN configuration of the CNV, and it's obviously an active CNV according to the criteria set forth by Professor Koskas with the loops and the complexity and so on and so forth. After about 2 years of injections, of many, many injections, you can see that the CNV burnt out, and you have this dead tree configuration of the CNV in exactly the same location, and you can see that this is no longer active. It's a burnt out CNV. Now, what is important, and one of the things that Professor Koskas' group is doing, is trying to find a way of quantifying the difference between here and here. By doing different things like fractal dimension analysis, complexity analysis, and so on and so forth, and they're going to be presenting that a little bit later. So what you have is, if you look at another CNV like you have right here, you have this central part of the CNV where the CNV grew out of the RPE and then spread out like trees with branches. The active part of the CNV is here, where you see the complex parts of the CNV. The not active part is right here where the trunk is. Now, if you take a look at this and you do a simple vessel density map, and you're just looking at the vessel density, you'll see that here you have a high density of vessels, and here, where it's very active, you have a lower density of vessels. So the vessel density map itself is not a good indicator of activity. So what we've been trying to do, or what I've been trying to do, is to, instead of looking at this binarized image to look to see for activity, I take a look at the skeletonized image. So I go from here and I skeletonize this, and then create a density map of the skeletonized image. And what happens then is that in this map you get a complexity map instead of a density map. And that gives you an idea that in this area, or in this area right here, it's a lot more active than in this area right here, where it's not active even though the vessels are very dense. And this, in the future, can hopefully give us an idea of what parts of the lesions are going to be more active and what parts of the lesions are not going to be more active. So far, so clear. This makes relatively good sense. The problem is that these types of lesions are not two-dimensional. They are three-dimensional. So if we're looking at this kind of lesion, and if we're looking at this kind of visualization, we've actually flattened a slab, and then we're analyzing that slab as if it should be just a flat plane. But it's not. It's a three-dimensional lesion. So all of these kind of structures are actually not completely correct. So in order to visualize this correctly, and in order to understand it correctly, we need to segment it three-dimensionally, analyze it three-dimensionally, and then we can have a much better understanding of the activity indexes of these diseases. So how do we do this? So let's go back to this one case we had. How do we do this? We do it with something called three-dimensional fractal dimension analysis. So in order to visualize what this means, I created this little animation of a three-dimensional fractal. So three-dimensional fractal calculations is something that's only been around since 2009. We didn't know it existed until then. But you can actually create this understanding, and it keeps going and it keeps getting smaller. The closer you get to it, the smaller the fractal dimension can be. And then you can analyze very complex structures. So if you have a low fractal dimension, or if you're not analyzing it very, very closely, you get this kind of a volume, and it's not very, very close. If you increase the fractal detail, it subdivides, and you get a lot more structure in it. And you can keep dividing it, and you keep dividing it, and you keep dividing it, and you keep dividing it until you get a very, very complicated structure of the polypoidal lesions, of the CNV lesions, of all the things that you're trying to analyze. But in order to do this, you need to do this kind of fractal subdivision of the analysis that you're doing of the three-dimensional volume. So obviously, this isn't a CNV. This is just a three-dimensional Mandelbulb visualization. So how do you do this when it comes to choroidal neovascularization? So let's go back to our case. So here again, you've got this case with the CFAN configuration. In the three-dimensional visualization, you see that these structures are a little more complex than is indicated by this flat visualization. So what I did was to try to create a segmentation method to segment this out, because right now this three-dimensional visualization in my software is just voxel-based, but we need to actually segment it so that we can visualize it correctly. So I created this. So this takes that data and segments it into triangle mesh segmentation, so it actually creates a real structure in the virtual world that can then be used for fluid dynamic simulations and a volumetric analysis to see what's going on with the structures. So I took that information and I combined it with something else I was playing with. As you can see, I like playing with my PC. And here you see a fluid dynamic simulation of blood that I created just to see if I could do it. Now, if you take that fluid simulation of blood and you mix it with the triangle mesh simulations, I wanted to see if we could get this to interact directly with the segmentations I got of a real patient. So I took this patient here, and this was a patient that just walked into a demo of the OCT, and we did a fundus image, and you can see he's got this weird little squiggly choroidal line right here. And I was trying to figure out why. So on the OCT-B scan, you can see that he's got a subchoroidal tumor. It's just a scleral bulge. But I wanted to see if we could visualize that little squiggly choroidal vessel that's being pushed up in a different way than we're doing right now. Obviously, OCT-A doesn't really work on the choroid because of projection artifacts from the choroid capillaris. But what I came up with is something that I call choroidal vasculography, where we use the structural data to visualize the choroidal vessels in very, very high detail. So we can see exactly what's going on inside these vessels, and we can see where this tumor is. We can see exactly where the vessels are and what's going on with them. Now, what I wanted to do was I wanted to take all of this information and see if I could segment this data in a way that I could interact with the fluid dynamic simulation I was doing before. So what happened? I took the data, I flipped the data, and inside of ImageJ, I did a threshold segmentation of the data so that I have an exact representation from here to here of where the vessels are. These vessels, I then created, out of these vessels, I created a point cloud with 1.5 million points, which was then meshed into the three-dimensional mesh in order to create a true representation of those vessels. Now, if you take that and you visualize it, you can see this. So these are the choroidal vessels of this patient with a subchoroidal tumor, and you can visualize exactly where all of the choroidal vessels are and where the spaces in between the vessels are. Now, this becomes very important because when we're analyzing pachychoroid and the different choroidal diseases, we need to know, is the thickening of the choroid related to thickening of the vessels, or is it related to thickening of the tissue in between the vessels? So with that, we can differentiate between different diseases. So this becomes a very important thing. But what I wanted to do is look at this vessel and see how close I could get to this vessel. And if you look at this animation here, you can get extremely close to this vessel. You can even go inside the vessel to see what's going on inside the vessel. Now, clinically, this has absolutely no use whatsoever, of course. But what I want to do is I want to see if I can give these walls physical properties so that I can use fluid dynamic simulations inside of this segmentation, so that we in future can do volumetric measurements and see also if changes inside of the vessel diameter will cause changes in the fluid dynamics inside of the choroidal vasculature. So what I did was I segmented out an area of this vessel, and I created a Navier-Stokes-based fluid dynamic simulation inside of this vessel. So it's based on inviscid fluids. And you can see that you can visualize exactly where all the particles in the fluid are going when they're looping back and so on and so forth. But to make it more clear, I removed the vessel around it and show only the fluid, and then you can see how the flow is. Now, the benefit of this system is that you can color code these particles to show different information. So on the one hand, you can do, for example, age. So you can see as the particles get older, you can see where they're going, so you can actually track the age of each particle and see where in the vessel it's actually ending up. You can also do flow density, so you can see that here is a pressure point, here is a pressure point, and here are vortices where it's rotating around and creating a vortex. So you can see what kind of flow problems that you're going to have inside of the OCT. With the program, it is also then possible to change all of the parameters inside the fluid. You can change the viscosity, you can change the flow on the walls of the vessels, you can change the elasticity of the vessels, so that we can get more and more of a realistic flow simulation inside the choroid. As said, at this point in time, this is just something I'm playing with the data to see if it's possible, but I think in the future it will give us a much better understanding of what's going on in the choroid and what kind of information we can end up getting from the choroid. So getting back to our original case, hopefully we'll be able to have a much better understanding and be able to quantify these differences so that we can really have a quantitative number on activity of choroidal neovascularizations. Thank you very much for your attention.